once again, the first step, we have to import stuff, import the information Python needs to do lots of the things we want to do. So run those import commands. It's a little bit slow again. And now we're going to give it the same composition that we used earlier, but I am inventing some concentrations for CO2 and water, because the melt inclusion composition we used earlier had already done a lot of degassing, I think. So we're going to think about something that's maybe closer to having a primitive composition of volatiles. I mean, the values I've chosen at random may be totally unrealistic, but they're higher, which is the main point. So 0.5 weight percent of CO2 and 1 weight percent of water. So we load that information in again, and now we come to calculating degassing paths. So this is what will happen if you have this parcel of magma. Maybe it's in a melt inclusion, maybe it's just in the conduit, and it starts to decompress and rise up towards the surface. We can predict exactly what will change about its dissolved volatiles and the gas that's in equilibrium with it. And we call the calculation in a very similar way. We calculate degassing path this time. We give it a sample. We have to give it a temperature to run it at. But now we've got this new parameter, which is fractionate vapor. And this means, do we want it, or when we exsolve some vapor bubbles, do we want those vapor bubbles to stay in equilibrium in place with the melt? Or are we going to assume that they move off and leave the system? So maybe ascend, or maybe the kinetics, we think the kinetics is just too slow for them to continue re-equilibrating. And I've set it to 0. So this is saying fractionate 0 vapor. Do not fractionate any of it. Keep it with the melt. So this is the equivalent to it being a perfect closed system. So we can run that calculation. The first thing it does is find the pressure at which degassing will start, and then it will start running the degassing path from that pressure. And one of the nice things about Python modules is there's tons of ways of customizing the calculations, because we're not limited by the number of buttons we can fit on a screen. So for example, one thing you could do is say, well, I don't want you to find the saturation pressure. I know what pressure I want you to start the calculation at. And there's tons of other parameters like this you can add in for all of the different methods. And the way to do that is like I said earlier, you type it in, put a question mark after and run it and see the output. Or go to the website I just showed you, which has all of that information there too. Or look at the right tutorial. So we need to pull out the result in the same way. And then we can look at the result. And now we have a list of pressures starting at almost 5 kilobars, where we have actually all of the volatiles we started with still dissolved. So almost a weight percent of water and almost 0.5 weight percent of CO2. And as the pressure drops, those start to decrease. But again, and we can now do an open system calculation. So this is where fractionate vapor is set to 1. So fractionate all of the vapor. It's repeating the same thing again. So it'll start from the same place, but this time, every time an infinitesimally small volatile bit of volatile mass is produced, it will leave the system. And now we could look at the table again, or we could just plot the results and compare the two. And so you can see that your open system CO2 drops far more rapidly than in the closed system, as people have seen before and is a well-known behavior. And you could go and play around with these calculations. You could start it at a different pressure. You could change the composition. You could change the model that's running it. And if you wanted to, you could plot them all together and compare it.